Welcome to the Industrial IoT Spotlight, your number one spot for insight from industrial IoT thought leaders who are transforming businesses today. With your host, Eric Walenza.
Welcome back to the Industrial IoT Spotlight podcast. I'm your host, Eric Walenza, CEO of IoT One, the consultancy that helps companies create value from data to accelerate growth. And our guest today is Christopher Nguyen, CEO and co-founder of Aitomatic. Aitomatic is a knowledge-first app engine for industrial IoT that helps industrial companies use their domain expertise to build more effective algorithms. In this talk, we discussed why only 9% of manufacturers currently use AI in their business processes and how they can overcome data availability challenges. We also explored which use cases a human-first AI development platform is suitable for and which use cases a traditional black box training approach works well in. If you find these conversations valuable, please leave us a comment and a 5-star review. And if you'd like to share your company's story or to recommend a speaker, please email us at team@iot1.com. Finally, if you have an IoT research strategy or training initiative that you'd like to discuss, you can email me directly at erik.walenza@iot1.com. Thank you. Christopher, thank you so much for joining us on the podcast today.
Thanks for having me.
So, Christopher, you have a really fascinating background, not just on the technology side, but also I think on the personal side. We won't cover that too much, but I would say you are very much an American melting pot success story. So coming over from Vietnam and then crafting a very successful career in Silicon Valley. We maybe don't need to go back all the way to your birth, but can you just give us a little bit of a walkthrough of how you ended up in the technology domain?
Well, briefly, I came to the U.S. as a refugee child from Vietnam back in 1979 and ended up in Silicon Valley basically at the beginning of the PC revolution. So it was hard to fall out of that. So I started hacking then. I was 13, and I have not stopped since, literally. So whatever that has happened in between is just one experience, hacking one system after another. But I've accumulated a lot of experience on the entire technology stack, all the way down to device physics and all the way up to software systems.
Actually, I'm curious there. How old were you when you arrived in the States?
I was 13.
You were 13 when you arrived, and I imagine. I've got to imagine that your English was maybe certainly not fluent.
No. My only foreign language at that time was French. That was my generation. You get to choose your foreign language track, and I think roughly 80% choose French, and English was sort of the weird one. So, but I learned here, and such as I guess the let me call it the strength of the American system, the American culture that you assimilate, right?
And when you say hacking, were you already as a teenager kind of learning how to program computers? And
yeah, so of course it has to be in the U.S. It was not in Vietnam, but. My first PC was my first computer, that we, my sister went to work and scraped up enough money. I think it was $400 or $500 at the time, which was a huge amount, right? It was a TI 9940, a Texas Instruments machine. It has no storage at all. And so you have to write the same basic program over and over again. I remember going to the nearby mall, Eastridge Mall, and there was the beginning of an Atari computer store, and I will be writing some programs there that does some cute graphics, and then people would crowd around and watch, and they would buy their computers for their children. So the store manager said, "Hey, come in anytime you want, right after school. You can just play with the system."
Oh, that's so cool. It's really cool how programming is kind of a universal language, right? Even before you really become fluent in English, you can start programming.
Yeah, I don't want to make to sound too profound, but I think it's what. How should I put it? Got me out of poverty, right? Yeah, I was able to do consulting jobs and so on. Yeah,
you got into Berkeley, you got into Stanford. When did you first? So were you already involved in kind of computer programming in your degrees, or when did you first start doing this more professionally?
So, such as the culture at the time, this is 1984, 88. was my undergrad at Berkeley. My computer science training is, of course, a combination of coursework, but even before that, I was already practicing a lot of computer coding and programming and so on. I ran the educational systems at Berkeley. We call them the vaccine, PDP-11, and so on. So, at the time, there was like 5 machines over the entire campus, and I was a sysadmin for that. That was my job in college. Going to computer science classes was more of a revelation that so there are systems and patterns and principles that people have thought about, right? So it's more my computer science education was more, think of it as an apprenticeship, right? You do before you realize that there are formulas and things. In many ways, I think it's actually the best way to learn, right? Do first and then refactor it out to principles later, rather than the other way around.
Yeah, so actually, I'm just seeing that you have then your master's and also your doctorate in electrical engineering.
Yep, that was Stanford.
The
That was in
best of both worlds.
Device physics, because at that young age, I was naively, look at the whole stack, and I said I want to work at the bottom of the stack so that everybody has to depend on me, and I have to depend on no one. So I went all the way down to transistors and electrons and holes.
Okay, well, IoT and AIoT has finally caught up with you, so we're bringing you back to the bottom of the stack now.
Yeah. We're back to atoms. Silicon Valley for the last 10, 20 years, my friend Mark Andreessen likes to say software is eating the world. But we're realizing that geopolitical risk, manufacturing, offshoring, and so on, turns out we do need to start actually making things again. So atoms are getting their day back versus just bits, right? So the Googles of the world is digital in, digital out. But the Panasonic, the Samsungs, the TSMCs, and so on, UMC, SMIC, and so on, right? You're absolutely right. It's their time to come back.
So I think we don't have time to go through your entire bio. You've worked with half of the tech companies in California, but maybe we can cover Arimo before we get into Aitomatic, because I think this is probably a very important part of the founding story. So what was the vision when you set up Arimo?
So in many ways, Arimo to Aitomatic is really one straight line, one project that I started in 2012. Arimo was acquired by Panasonic. After we got initial product market fit and worked with various customers, one of the largest customers turns out to be Panasonic. We also worked with NASDAQ, Kohl's, other entities, even the intelligence agencies, and so on. At the time, the company was really, I would say, a bunch of geeks with algorithms. And Panasonic wanted to acquire us because 2018 was the 100th anniversary of the company founded by Matsushita Son. And the idea was to transform Panasonic from, we say roughly from hardware to software, but it's really moving up the vertical stack, right? You may know that Panasonic makes a lot of the industrial equipment, cold chain, avionics, automotive, and so on. And AI was one of the major missing pieces to position the company much closer to the CEO level, the customer. So that was the rationale for the acquisition, and we learned very quickly after the acquisition that a lot of our systems and techniques that were optimized for the digital world didn't work for the physical world, and I can talk a lot more about why that's the case. And then for the better part of the last 5 years, we basically built up a lot of knowledge and experience, ran into a lot of walls, and found solutions for them, which we've launched out of Panasonic now. And Aitomatic is about refactoring all of that knowledge into a product to help industrial companies with AI.
Yeah, and understood then that Arimo was acquired. You then ran the business under Panasonic for a number of years, and then I think just last year set up Aitomatic. Let's get into the problem here. So we have now fairly mature AI frameworks. We have good sensor infrastructure. We have good infrastructure for managing large data sets. We have a lot of platforms on the market. Why in the industrial space are we not seeing AI take off as we are seeing it in some of the consumer markets, at least in kind of back end processing? What are the challenges that still need to be solved here?
Yeah. Well, you actually hit the nail on the head in our earlier chat, which I'll go back and let me answer your question by starting out with the general principle, and then I'll give a specific example of that. And this is something that took me the better part of a year to come to reconciliation with, right? The general principle is that there's something very fundamentally different between the digital versus the physical domain, right? I like to refer to that as bits versus atoms, right? For a company like Google, right? When I was running Gmail infrastructure at Google, data, the input was data, the output is data, and the processing is all data. And any experiment that we wanted to conduct is done digitally. Is done, sort of in cyberspace, right? And we can launch it at scale. And you launch it in the morning, and by afternoon, you've got millions and millions of, let's not use the word examples or data points to work with. In the physical world, things cannot move as quickly, right? And you mentioned, for example, if you're going to predict errors and failures, but you don't have that many errors and failures, certainly not happening at a rate high enough for machine learning to consume. So that's the fundamental difference between an industrial company, trying to take advantage of AI versus a digital first company, which is companies that were created in the last generation. I would say from 2000 onwards. And so, a particular example, right? Let's take predictive maintenance. This is something that anybody in manufacturing, anybody in industry, say that's the holy grail. That's what we want. So let's consider what is really predictive maintenance. Well, in the old days or even now, we have what's called reactive maintenance. When something breaks, you fix it. But that's actually very expensive. It's not just the price, the cost of the equipment and the cost of the repairs, but the cost of downtime. And in case of automotives, maybe safety and human life is at stake. And so the next stage is preventive maintenance, right? That's what aircraft MRO is. Every 6 months, every period of time, you go and you inspect and you replace everything, whether it's broken or not. The holy grail is predictive maintenance, meaning you only replace things that are likely to fail, right? But that requires prediction. That requires the ability to say, to answer this very precise question, which is, for example, over the next 2 months, right? Give me the list, the probability that this particular compressor in this refrigeration system is like to fail. And if it exceeds 80%, I'll replace that particular one. Machine learning requires, in order for it to make that prediction, requires a lot of examples of that past failure. And it's not just the failure, but it's also stratified by what is the model of that equipment, where is it operated, what is the workload, what's the climate like, right? For example, we have applied use cases in supermarket refrigeration systems. And so by the time you stratify by these physical parameters, you end up not having enough what's called labels. In machine learning, you need a lot of what's called labels. You don't have enough of that in the physical domain. So it's what I call the small data problem. And people working, trying to apply AI to this domain is starting to slowly realize that. Of course, we were in a way fortunate and unfortunate to run into it, as early as 5 years ago, because we were part of this industrial giant Panasonic. But it is now becoming a well-known problem. And so the question is, how do you solve that?
So let's discuss more what this actually looks like in person or in practice. So if I have a production line and I have a motor on the production line, and this production line needs to have 99.x% uptime. So this motor breaks down once every 2 or 3 years. So basically, I have no data to train on that are kind of indicative of what conditions look like when the motor breaks down, because it never breaks down. But if it breaks down, then it's a multi-million-dollar problem. So I'm willing to invest in a solution to predict breakdown, even if it only happens every couple of years, because it's such a big problem. But I can't do it because the data never accumulates. So so you say tagging is the solution, but there we still lack. I guess we lack data to tag. So how do you address that challenge, that fundamental challenge of dealing with very small data sets and around issues like a fault in equipment?
Yeah, I would say that tagging or labeling is not the solution. That's what we we meaning including myself, because I've been a professor at UST where we teach our students. We machine learning people think about labeling, right? But you don't have enough labels. So the solution turns out to be a blindingly simple and straightforward insight. But we can talk about the actual implementation of it. The insight is and we do this. Let's follow the use case of refrigeration predictive maintenance. The initial solution we built after the acquisition, after the integration into Panasonic, was what's called anomaly detection. Meaning, I cannot tell you, what's likely to fail over the next 2 months, but I can tell you when something looks different, when the sensors are not setting off the same signals as they used to. That can be done, right? Because I don't need failures to tell you that something looks different. The challenge or the limitations with that is that anything could be the cause for something looking different, including, you have different workload today, or, somebody decided to turn off one system. And so the signals, the sensors look different. And so our first solution was to use anomaly detection in order to shortlist things for an engineer to look at, an expert, a domain expert. And the domain expert, we watched them, do this work, and they're surprisingly good at identifying potential issues down the road, including their ability to say, this is nothing, don't worry about it, right? But that gets tedious for them after a while. And the blinding insight is, what if we just codify the heuristics that this expert is going through, and then automate that, right? Capture their knowledge. Because if you think about it, what they're using is their 30 years of line experience that is not in the data coming from the sensors. So the key idea here is to be able to combine human expertise, domain expertise, that these industry companies have a lot of, right? Combine it with the data, and then come out with an overall AI solution. And so that's what we do. We actually have a branch of AI, if you will, that we're advocating called knowledge first AI, right, as opposed to data first.
Yeah, I think that's a really interesting way of framing this. If you think about a lot of the, kind of the pure data environments, right? If we look at finance, for example, you can have quants that go into Wall Street that fresh graduates, and they might not understand anything about finance, but they understand how to manipulate data and monitor data, and they can be very effective, in some cases. And of course, over time, they learn kind of the finance, but basically they can be effective just as quants. And I think in the industrial space, that's not really the case, right? You need this domain expertise on the kind of the messy mechanics of the physical environment, which means that not only do you have a very challenging problem to solve from the technical standpoint of having limited data and messy data, but you also have a more challenging human environment where you have a 50-year-old engineer who's been working at the plant for 25 years, and he can listen to the machine and he can make sense of what's happening, and he has a tremendous amount of intuitive know-how. And then how do you kind of embed that in an algorithm, right? That's kind of the challenge at hand here. So how do you think through this, not just the technical standpoint, but issue here, but also the kind of the human issue of getting these very different teams to collaborate effectively on building a solution?
You mentioned quant. Believe it or not, I happened to be CEO of a quant shop in Hong Kong between 2000 and 2005, quite successfully. So when I say it's different, it is different. So you're absolutely right, and because of this physical domain. So the question, how do we? So this sounds right, all right? In fact, it is. It's really interesting in that I don't have to, a lot of these customers of ours. I don't have to convince them of this, right? They know it intuitively, right? They know that they have a lot of knowledge, and they know that the data that they have, because they have data scientists, they've hired these people, and somehow there's this barrier between what they know versus the data that they have. They already know this setup, right? So the key is, okay, so how do you put all of this together? So that's the product that we're building to automate what I'm about to share, which is in principle, if there's a way for a domain expert to say, in the case of, say, time series data, if this temperature is rising and yet the pressure is remaining constant, right? And they can give the ranges. Then take a look at this other issue. And then once you look at that, to try to combine. In other words, it's sort of a heuristic that they go through. In principle, you can simply take Boolean code, logic, and encode it. And so that is one of the earlier approaches that we take. But can you take it all the way to a situation where you can take what I just said as natural language and then generate that code automatically, right? So from the verbal description or from the written description, can we take that and somehow intelligently generate the code, which may be in Boolean logic or fuzzy logic? I think you and others will have heard of some of these systems. It's not that the codification doesn't exist; it does. But how do you bridge that between human natural language or somebody's experience and the encoding? So that's what the product that we're building is. And once you have this, what I call the knowledge model, then instead of using labels, which you do not have, you can use that knowledge label now to train machine learning models. And then you can combine the two models in what's called an ensemble. And the ensemble is kind of like this very smart combiner. It knows when to listen to the knowledge model more than the machine learning model and make the best decision possible.
Okay, fascinating. So let me see if I'm kind of thinking about this correctly. The traditional way of programming that we might have used 10 years ago, in many cases still are using today, is to try to translate someone's experience into a calculation. If X goes up and Y goes down, then Z happens. And we come up with these very rigid rules that can work, and they're understandable by humans, but they're often fairly simple. And then we have machine learning, where you put a bunch of data in a box. The box, the algorithm is kind of auto-generated to some extent, and then it spits out another equation, which is much more difficult for us to understand and sometimes can extract a lot more insight, but requires a lot more data. And you're basically combining these two together. You're saying let's build the knowledge map, and then let's work with and basically use that to. Are you using that to train the AI algorithm, or are you generating a new algorithm that kind of switches from one path to another depending on what seems to be more likely to to identify the right solution? How you can tell I'm not probably sufficiently technical here, but help me understand how to think about working with these two together.
Your intuition is exactly right. So I like to I like to say that the human rules are very good in the center, meaning near the normal operating regimes, right? They tend to fail catastrophically at the edges, in the exceptions, right? Whereas the machine learning, if you train using that model, tend to be smoother at the edges, right? But they may not be as good without labels near the center. So it is the combination of both that human knowledge model and the machine learning model that is trained by it. That's why the ensemble works better than both individually.
Okay, got you. Maybe we can get a bit more into the Aitomatic product now, since we're talking more about how this works. So would this be, would it be a platform where you would have access for engineers, maybe mechanical engineering or different teams to embed their knowledge? What would this actually look like from a user perspective?
Yeah, from a delivery point of view, you can think of that as any other SaaS software platform. You probably use Gmail, which I used to run at Google, right? You don't worry about where the infrastructure is. You just open up your web page and you start using it. So the idea here is that with Aitomatic, there's a tool. Again, you point your browser, of course, at a secure web page somewhere, and then you give it instructions, right? Human instructions, and then somehow, in our software, it generates models, right? Basically natural language in, models out. And the models, there's a number of sophisticated architectures that we have created. The one that I've described, where we have a teacher, which is a human knowledge model, a student, which is machine learning that gets ensembled. We call that the K Oracle architecture. The K stands for knowledge, and we have a host of others that are useful for different use cases. But a customer of ours, their team, what we call them AI engineer, they would interact with the system and generate these models, and these models go into a system application, which we also host, and they can launch that and manage it directly from their cloud or our cloud. The deployment is very flexible, but access to this software is through that SaaS model.
Okay, and so the users, I'm imagining you're going to have some data scientist or somebody who has data science expertise who's going to be a primary user, but you're also going to have very critical domain expert users who, if I'm that I'm sitting here in Shanghai, and if I reflect on, maybe a large manufacturer in northern China, they might be relying on a lot of people that are in their 40s, 50s, who maybe in some ways are quite savvy in terms of using mobile phones to manage their lives, but might spend very little time actually on a computer and not really have much expertise there. So how do you so first, who would be what would the user ecosystem look like, and then how do you engage the non-technical people to make sure that they're able to efficiently embed their knowledge into this framework?
Right. And to be sure, this is not consumer software, right? This is enterprise software, right? So when we say the domain expert, they are expert, they are engineer. They just don't happen to be AI engineers, right? And so our customers typically, have large teams and they have different roles. There's invariably somebody who knows the domain very well. They may or may not be able to code at all. In fact, I'll give you one example where we have a use case in China where there's a large supermarket chain, and they are opening about over 1,000 stores per year, right? Over 100 per month, and they're using this system, right, to build what's called a forecasting for decision making. For example, forecasting what the inventory should be, what the revenue might be, to determine exactly the location where to open the new store. Doing that by sheer human estimation alone is overwhelming in terms of the amount of input that they have to consume, but also very error prone. And yet, the local managers are very good at sharing their knowledge. Like, there's a subway station on the right hand side of that. And if it's more than 100 meters away, then the foot traffic may drop off in a certain way. And some of that knowledge is unique or certainly applicable only to that locality. So those people, those local managers, would be able to work either with our solution team or more likely their own AI engineering team, and they would actually be saying these things, right? Then these things are then input into our system, and that natural language input will be translated into code automatically. Of course, somebody has to review that code, right? To review the output of that system. But for the most part, you can think of this system as, going directly from that human knowledge description to a bunch of models that does that prediction. And you compare the performance of that against something that has no such human knowledge input, but you try to do typically what data scientists do today. Give me, in this case, POS or point of sales data from the past, and then give me information about the geography, the map, and so on. And invariably, when you add that human knowledge model, the prediction becomes better. And we can measure that. We can measure that in terms of what's called the mean error of the prediction.
Yeah, I think this forecasting use case is quite interesting. Every company faces it, but with different dynamics. Maybe I can throw a problem by you, and I'd be interested to hear your thoughts on whether your solution could actually address this. So this was something we were working on a couple of years ago, and it was a large chemical company, and their situation is that they have to manage supply and demand because there's periods in the market where there's more supply than demand. There's periods when there's more demand than supply. Supply cannot you can't shift it very quickly, right? You have a certain number of facilities that are running, and adding new ones takes a lot of capex. And their forecasting was always terrible, right? It was like 60% would be considered a good target. And this makes it very difficult for them to set prices, right? Because they have to forecast to set prices. So they wanted to look at machine learning to address this. But then you have these some things where machine learning is probably good at. So correlating things like housing starts in Japan and car sales in the U.S., et cetera, that all then work their way up the supply chain eventually to the demand for their materials. But then you have other things like if there was a fire at one of their competitors' factories and it shuts down for 3 months, then all of a sudden there's no way that the algorithm can manage that because that happens every 2 years. But when it happens, it completely disrupts the industry. And that we really struggled with using a pure ML approach because there was, occasional events like that completely confused the algorithm. And so how would you look at kind of addressing a challenge like that? Because I think that's actually a fairly common challenge that industrial companies have.
Exactly. And I'm not here to say that this approach solves every possible problem out there, right? Or even is superior to every case. If you're doing, Google advertising and trying to predict the likelihood of a click, you have lots and lots of predictive data out there. You don't even need to know why, right? I remember when we were testing different colors, the background of the ad, and it turns out, the best background color was a little yellowish, right? And because it was predicted by data or measured, I would say, not even predicted. And so, Sergey Brin used to say, that looks like piss, right? But it is what it is. But you're right. An industrial fire, right? Give me a time series data, of all the fires that have happened and their impact. You don't have that data set. So this is a case that we have actually done, are actually doing in a very similar way. There's a use case where we're trying to forecast for these industrial devices that are being manufactured by a large conglomerate, and they're always trying to get ahead of competition, right? If you're making capacitors, how much volume should I make in terms of the 10 microfarad versus the 25 microfarad? Decisions like that, but in a predictive manner, getting ahead of the market. You can't do that by forecasting from time series data alone, precisely because of things like that. And yet, very often in many of these cases, when you ask a manager who has lived through enough, and you ask them if there's such a fire, or now that there has been such a fire, what do you think demand will be affected by? And they can say, I think it's going to be down by 20%. They could be wrong, but it's going to be a heck of a lot better than a machine learning model that is completely unable to take into account for that, right? So intuitively, you see that this can be better. Then the next challenge becomes, how do you incorporate that knowledge into the system in such a way that is not a different system, right? And so the tool that we make provides our customers with a way to do that.
So if we think about the use cases, as you said, that there's a lot of things that traditional ML does really well. If we think about the use cases that require more kind of a human input in the training process, what would those be? So we have demand forecasting is one. Anything related to predictive maintenance, or I guess predictive analytics in situations where there's uncommon events could be another. What are the other things that have come up on your radar as key use cases to explore?
Right. So again, I'll give a principle first, and then give you more examples. The key principle that we have learned is just what we discussed. If your intuition is such that if there's a human expert who can add more light to this problem due to their life experience and so on, and it could make a predictive difference, then that's a very good candidate for this kind of thing. And when you go across that, you tend to find that it tend to be physical problems rather than, for example, the Google ad example that I shared with you. I've given you a number of examples ranging from predictive maintenance with refrigeration to predictive forecasting and so on. There's another use case completely different, which is there's a global marine navigation company that we work with. If you go here, I live in the Bay Area. If you go to Half Moon Bay at the marina, you look at all the boats, and 70% of the masts is their brand. They also make what's called fish finders, which shoots out a sonar beam straight directly down to the ocean, and then the echo comes back, very, very much like submarine technology. What comes back is an echogram. And guess who is really good at reading these echograms and be able to tell you that's a school of macro right there. And somebody might say, well, you sure it's macro and not sardines? I say, yes, it's macro, trust me. It's not the engineers, it's the fishermen, right? The fishermen that have used this equipment for 5-10 years, after a while, and they're good, by the way, only in their area. So, for example, in the case I'm thinking about in my head right now is in Hokkaido, right, and macro. And so this company knows intuitively that if we work with these fishermen and somehow codify whatever they're seeing in these images, right? And there are not a lot of them, right? So you cannot label millions of these things and somehow capture what they're seeing. They might say, if you see this golf ball shaped thing right next to this stick-like thing, right, on that echogram, which to you and me looks like a mess. But when you say golf ball, and I said, okay, I kind of know what golf ball looks like, and we could codify that experience, then what happens is that this fish finder, which the market is only for say 10,000 of these expert fishermen in Japan, suddenly the whole addressable market becomes 10 million, because you and I don't have to interpret these echograms directly. We can just by the benefit of this algorithm that we encoded, it just labels macro, and then you just basically throw your net down there.
Okay, interesting. And actually, that maybe raises another question of the kind of ecosystem of AI algorithms. So one other way of addressing this dearth of data is to look at how we can share data between different companies, obviously highly anonymized, but maybe one factory has a certain number of motors, and those motors only break down so often, but then those motors are also deployed in a lot of other factories. And so in aggregate, there's actually maybe a lot of data. It's just that in industrial, data tends to be highly kind of firewalled from other systems. Is there any mechanism that you use to or are considering using to enable the exchange of this insight or this expertise, so that customer 10 can use the insight that was generated from customer 3? Or do you have too many kind of privacy and legal issues there?
Yeah, I think the opportunity is one level higher. There's a wise and not so wise saying that I don't like, and I think is completely wrong, that says data is the new oil, right? And that implies that is inherently valuable and fungible and so on. And as this discussion shows, 1 megabyte of data X is not at all the same as 1 megabyte of something else. I think the opportunity is in sharing models and not in sharing data. And sharing could be selling, right? If I have a model that can predict or classify mackerel versus sardines in Hokkaido, I can sell that as a model or a prediction service. And this is starting to become a business model for some companies. There are startups in the US that are dealing with this in the easier, more available model set, sort of, for example, image classification and so on. I think increasingly companies will find opportunities to, essentially encode things, knowledge and data into models, and then they will sell models. And in fact, in terms of the progression of machine learning, 10 years from now, we'll look back and realize that this data-driven or data-only machine learning is actually the very basic step. It's almost like semiconductors, but at the transistor level, right? And then we go to LSI, large-scale integration, very, very large-scale, ultra-large-scale, and so on. And then we deal with things as blocks rather than individual transistors. I really believe that knowledge-based training of models is the future, right? These models will get smarter and smarter. They will understand what golf ball means, right? They will also understand English, Chinese, and so on. So that's where the future is, and what we're working on is the beginnings of that next stage of artificial intelligence.
Okay, great. And I know also Aitomatic is still a relatively young company, I guess, in your second year, although, as you said, it's really an extension of work that you've been doing personally for the past decade. So there's a lot of know-how behind it. But from a development standpoint, what is in the future for you? What do you look at over the next, let's say, 24 months in terms of roadmap for new functionality, new features, new use cases?
Yeah. So as a company, we're at an interesting point. There's a phrase called product market fit, right? Which is we're trying to make sure all these ideas that I'm very sure are correct, but then are they correct and needed over the next 6 months, or is it over the next 6 years? You could be right and completely off the timing. So we're fortunate in that we have, after we launch out of Panasonic, we have a lot of existing customers, and we actually call them design partners today, right? And then we have also won other contracts and so on. So we're working with a fairly large for an early stage startup, something like over a dozen different customers and use cases. So really, the next 12 months is iterating with these design partners into a product set that they find, yes, this is what our humans can work with, right? This is what our domain experts can work with, together with our AI engineers. And while you can imagine all kinds of use cases, only 3 or 4 are going to be profitable. It makes sense over the next 12 months for the industry. I like to say, people like to say, the future has arrived. It's just unevenly distributed, right? So there will be leading use cases, and the use cases that we're seeing resonate the most is industrial equipment predictive maintenance. That's one example. So over the course of the next 24 months, what I want to get the company to is, of course, expanded revenues, but also, quite importantly, a well-defined functional set. No more, no less. Don't overbuild, right? That satisfies our customers, and that's something that we can make generally available to the market.
Yeah, I'm curious, just as a serial entrepreneur, or somebody that's been involved with a lot of different technology projects, how do you think about the tension between focusing on a specific market and building a product, for let's say one use case like predictive maintenance for industrial equipment, versus building more horizontal technologies that can apply and kind of apply basic principles to multiple, potentially very different use cases that all share similar features? Because I guess there's forces pulling you in both, right? On the second hand, you have a much larger potential market. On the first hand, it's easier to define a product that fits a particular set of customers. As an entrepreneur, how do you view this challenge?
Definitely focus. There's no such thing as saying, let's try to address everything and capture a large market, because there's always somebody else who's going to do it better than you. Now, focus doesn't mean betting on one thing, right? Like I say, product market fit means being humble about how much you really can predict, right? Like, I'm very convinced, I'm very sure about this vision, I'm very sure about the technology that we have. But do we really have a product that people need and will pay for, immediately? And so it's in computer science, we call that the exploitation trade-off, right? So the idea is to, again, of course, try to understand the industry as much as possible. So we have the advantage of coming somewhat as insiders, right? So that's an unfair advantage that we have. And then you have to experiment over a set of 3 or 4 use cases, not 30, but also not 1. And that's why I'm able to tell you now, for example, that some use cases we already have traction. Believe me, we have tried some other use cases for which the market is not that interested yet, right? Or for one reason or another, our customers are not profitable on those things. So what's the point of saying that we're going to do those things? So that's in a way the answer, the structure of the answer is very simple. The challenge is the judgment, right? It comes down to that judgment, and I think experience and conversations, right? Talking to your customers helps tremendously. This is not an exercise where you got 10 smart guys inside the office talking to each other.
Yeah, that's right. This is something I've personally identified. I have an issue with, right? It's easy to brainstorm ideas, and
that's right.
And then in the end, having some degree of success means really focusing on those. But it's a challenging thing to choose bets, right? Because it does require you devoting a lot of time and.
I like to say, respect the challenge, right? I don't think you're so smart.
Yeah, that's right. Great. Well, Christopher, I think we covered a lot of ground here. Anything else that folks should know about Aitomatic or about the problem here?
I think we've certainly covered a lot, other than the fact that you could hear the excitement behind my voice. I think over the next 5 years, we're standing at the threshold of what I call I'm going to go on the record and say there's a shift back to atoms from bits, right? And again, even Mark Andreessen has recently blogged how we need to be making things. It's time to make again, right? This is somewhat of an American-centric approach, message as well. But the events of recent years have highlighted the fact that we've offshored too much, and we've given away or sent away a lot of the muscles, while we focus only on the brain in the U.S. And so, semiconductor tooling, making things. I think it's an exciting time to be in the physical space, certainly in the U.S. and I think even around the world.
Yeah, absolutely. I agree 100%. Well, two very quick last questions for me. The first is, as a relatively early stage company, do you have any funding rounds coming up because we do have actually a number of investors listening here that you would be open to, external participation in?
Yeah, so we're very fortunate that number one, we started out with customers already. We have revenues. I'm also fairly reasonably well connected in the Valley, and so we've already done quietly, some rounds of funding, but never say never. So we're always opportunistically talking to folks and trying to time things. I think we have good metrics as a startup. So if anybody is interested, feel free to reach out to me, and then we'll talk.
Okay, wonderful. And whether it's around investment or around partnership or becoming a customer, what's the best way for folks to get in touch with you or your team?
Absolutely, the most valuable thing right now is design partnerships. Right, that's more important than the next dollar of investment. I think Aitomatic.com is a good way to get in touch with me. That's our website. Our company is just like Aitomatic, except starts with AI. So Aitomatic.com.
Great, Christopher. Thank you.
Thank you.
Thanks for tuning in to another edition of the Industrial IoT Spotlight. Don't forget to follow us on Twitter at IoT1HQ and to check out our database of case studies on IoT1.com. If you have unique insight or a project deployment story to share, we'd love to feature you on a future edition. Write us at eric.walenza@IoT1.com.